Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable Energy Technology Program. This is RET 120 Hydraulics. Today we're going to discuss some of the fundamentals surrounding hydraulic systems, and we are going to discuss Pascal's Law. First and foremost, why do we use hydraulics and fluid power systems? Well, there's certain advantages to them, and what a fluid power system is basically the use of a liquid or gas to transmit energy. And we're going to typically confine ourselves to the liquid, which is a hydraulic system. Gas, that's a pneumatic system. And we're going to spend more time talking about hydraulics. Again, its function is to transmit energy. So we all know that energy can neither be created nor destroyed, only change forms. So why are we using hydraulics? Like say, for example, we have a mechanical operation. We want to lift something. Well, why don't we just lift it ourselves? Well, you might not have the sufficient strength to lift this object, or it might be an incredible distance from you. Okay, so typically what we have is basically a cascaded series of systems used to transmit energy, and one of them being hydraulics. So this is a very simplified version right here. I'm going to take mechanical energy to turn a pump that creates fluid flow, i.e. hydraulic. These are all, I'm putting mechanical energy into a pump which creates hydraulic flow, which is, let's say, lifting some object. Again, why didn't I just use my mechanical force to shortcut to lift it? Well, maybe I can't. Okay, so maybe by myself I can't. I'm going to require some mechanical input to this pump. So what you're seeing is a cascaded system where there's certain inefficiencies in the conversion of this energy. So you're losing some energy as you come through. Still, you are gaining something in the fact that you have performed work. Okay, so think about this here. I've got an electric energy which is going into, I'm just kind of expanding on the same system, which is going into a motor, which is again going into mechanical energy, which is going into my pump, which is doing hydraulic energy, and now it's performing some mechanical lifting or crushing. Okay, so you're adding systems to these. There is a loss of efficiency. It says this is 96%. That's 96%. That's 96% from this initial source of energy, whatever it may be: wind power, nuclear power, coal power. Again, think about the chemical reactions that are occurring in coal and burning. Is all that energy transmitted to electrical energy? No, it's not. It's a cascaded system. You think, okay, everything's 96% efficient. That's good enough for me. Well, the answer is 96% times 96% times 96%. It's basically only 88% efficient. So a cascaded system, you're going to link up these inefficiencies from this initial source of energy. So I just want you to be aware that you're not getting something for nothing here too, if you do have to go to a hydraulic system. But why are we going to a hydraulic system in the first place? Well, there's certain characteristics about hydraulic systems that are desirable. Number one, they have incredible ability to perform work. They can lift heavy objects. they can lift them extremely precisely. So they're precise, they're powerful. And what's the coolest thing about the hydraulic systems? They're incredibly stable and solid. And that seems like a weird word to use when we're talking about a liquid to transmit energy. And when I say solid, I mean they're incompressible. So what this means is compression. A confined fluid, we're leading up to Pascal's law, by the way. I pour liquid into here, and I confine it by means of a top on this thing. And again, here's my liquid here. And I go ahead and put an incredible force on there. I might as well be pushing on a rock because, for all intents and purposes, liquids are incompressible mediums. So basically, I've gone into a stable hold position, and as long as there are no exit paths from this vessel that I put that in there, I could hold up whatever I want to. Okay, so it's really neat. A hydraulic system is capable of not only lifting and a great weight, doing it very precisely, it can also hold great weights. Okay, so what I'm leading into, as I mentioned earlier, is Pascal's law. Pascal's law is basically what makes hydraulics happen. And so Pascal's law stated is basically pressure is distributed undiminished throughout a closed container. So the unit of pressure we're typically going to see is pounds per square inch. So let's say I have a square inch of area, 1 inch on that side, 1 inch on that side, and immediately below it, I've got this square vessel that's holding some water right here, or whatever it might be. And it's inside this also cubic shaped box. And I apply a force of 80 pounds. So it would stand to conjecture, if it's following Pascal's law, which it is, because this is a fluid trapped inside an enclosed container, pressure should be distributed undiminished throughout this closed container. So how much pressure am I applying? I am applying 80 pounds over an area of 1 inch squared. So what is my pressure? 80 pounds per square inch, or 80 psi. So again, I've applied a force of 80 pounds to an area of 1 square inch, and I get my pressure. F divided by A equals P. So what's really neat about this formula, F divided by A equals P, if I wanted to solve for force, multiply times A, both sides, force equals PA. This can also be rewritten in our very familiar Ohm's law triangle. So if I want to solve for area, it's force divided by pressure. Okay? So let's say I'm experiencing a pressure of 100 psi on an area of 2 inches squared. What is my force? So I've got P, got A, multiply them together, 100 psi, so times 2 inches squared should give me 200 pounds. What if I applied that same pressure to twice the area? 100 psi times 4 inches squared. 400 pounds. See what's going on here? It's the same pressure, but I just increased the area, thereby increasing the force. This is a neat thing called a force multiplication system that makes use of Pascal's law. So, making use of Pascal's law, imagine, if you will, the following. Here's a tiny cylinder hooked to another cylinder via a passage. And this cylinder has a larger area. And I apply a certain force to this disk of area 1. Force 1, area 1. This fluid inside here, according to Pascal's law, experiences that pressure in all directions undiminished. But because of this little tube right here, according to Pascal's law, experiences the same pressure, undiminished in all directions, including up. Acting on this surface area here, A2, which is substantially larger, implying force 2 will be larger. Again, this pressure is equal throughout all of these interconnected passageways because of Pascal's law. So let's put it in some numbers here. Let's say a force of 200 pounds is put on an area of, let's say, 4 inches squared. What is the pressure experienced in this chamber? According to our little triangle, FPA, solve for P, it's F divided by A. 200 pounds divided by 4 inches squared should give us 50 psi. So that's the pressure for this chamber. But according to Pascal's law, it's also the pressure inside this chamber right here, 50 psi, acting undiminished in all directions. On an area, in this particular case, let's say of 8 inches squared. So 50 pounds per square inch is acting on 8 inches squared. What's the force? F2. F2, so we're going to solve for F, pressure times area, 50 psi times 8 inches squared should give us 400 pounds of upward force. So even though we applied 200 pounds of force in, we got 400 pounds of force out. That's what's known as a force multiplication system. And I know some of you guys are thinking, yeehaw, why don't we do this all the time? This is getting something for nothing. Well, not really. Because if you think about this, let's draw our little diagram here. Think about this in terms of 3 dimensions. If I push down on our disk at the top of this thing, and I've moved it down 1 inch, that means 3-dimensionally, how much fluid have I displaced? Well, if the area of this first one was 4 inches squared and I moved it down 1 inch, that means I've displaced 4 cubic inches of hydraulic fluid, meaning I can only go up 4 cubic inches of fluid. But look at how much bigger the surface area is. So, how far up will a disk of, in our particular example, 8 inches squared go when there is 4 cubic inches below it? And the answer is a ½ inch. It's going to only go up half the distance. Yes, it's going up with twice the amount of force, but it's only going up half the distance. So you're not getting something for nothing. It's a trade-off. Because basically, though I've increased my force, the distance at which that force is applied is less. So if you increase the force, you got to decrease the distance. And this is what's known as energy. This is a super important concept to understand. So energy is force applied over a distance. In SI units, the unit of force is a Newton. The unit of distance is a meter, so a Newton meter. In the Neanderthal system, unit of force is a pound. Unit of distance is a foot. Okay, so you aren't getting something for nothing. Yes, it's a trade-off. Yes, you've increased your force, but you've decreased the distance using a force multiplication system. So energy is in direct contrast to the next principle, which I'm about to talk about, and that is power. Power is the time rate of energy production or dissipation. Okay, so if it's the time rate, it's per second. You know, think about the miles per hour again. So if that's time rate, and so it's energy per second, in the SI system, that's a Newton meter per second. In our English system, foot pound or pound foot, whatever you want to call it, foot pound per second. Okay? And what's neat about these things here, there are certain shortcuts everybody knows. 1 Newton meter is 1 joule. And by extension, that's 1 joule per second. We all know 1 joule per second is also called a watt. So these are SI units that we're commonly use, our joules and our watts. Okay, again, a joule is not equal to a watt, and a watt is not equal to a joule. Foot-pound per second is not equal to a foot-pound, okay? Two totally different things. So say for example, let's just do a super quick example here. I've got a 4,000 pound car or weight that has been lifted by a hydraulic system 8 feet. What is the energy it took to do this? How much work is accomplished? Energy and work, they're the same thing, by the way. How much work is accomplished? Energy is the capacity to do work. So 4,000 pounds times its distance, the force times its distance, 32,000 foot-pounds. If it accomplished this in 5 seconds, how much power? Okay, so that is if it did this in 5 seconds. So it would be work or energy per time. So 32,000 foot-pounds in 5 seconds, 6.4, whoops, excuse me, 6,400 foot-pounds per second. Okay, which is not necessarily the prettiest units, 6,400 foot-pounds per second. That's why we have to call into another unit here, which is very commonly used. And that's a horsepower. So they're not equal, by the way. A horsepower is equal to, so 1 horsepower is equal to 550 foot-pounds per second. So I want to convert my power for that system into horsepower. So again, this is our unit conversion trick. 6,400 foot-pounds per second. And I want to convert it to horsepower. So that means what I want on top, 1 horsepower. What I want to get rid of on the bottom, 550 foot-pounds per second. Because again, I'm multiplying by 1 in this particular case, because 1 horsepower does equal 550 foot-pounds per second. These units cancel out. I'm left ultimately with horsepower. I still have to divide by 550, 6,400 divided by 550. It's giving us an example for this one is 11.6 horsepower. If I lifted a 4,000 pound weight in 8 feet in 5 seconds, I'm going to need an 11.6 horsepower system to go ahead and do this. Okay? So life is, again, not as simple as some of these examples that I just put out here. Let's go ahead and give you a super complicated example that's going to make use of all the tricks that we've learned thus far. Here, a cylinder of diameter. Notice I'm not giving you the area straight up. Diameter, 2 inches. Is again hooked in a forced multiplication arrangement with a larger cylinder of radius 3 inches. And let's say 400 pounds of force is placed on the smaller cylinder. And we compress this. We have a travel of, let's say, 1 inch. How much work can this secondary cylinder accomplish? And, oh, by the way, it's did this operation in 2 seconds. So I want to know the energy, work, and power. Okay, so feel free to go ahead if you feel capable of doing this. Go ahead and stop this thing, give it a try, and we'll be right here waiting for you with the answer. Okay, so this is how we go ahead and do it. First off, don't freak out. You've got all the techniques you need to solve this problem. Figure out the areas in terms of diameter and radius. What's area 1? Area 1, pi over 4 d squared. Area 2, pi r squared, or you could convert it to a diameter if you wished. What are our areas? You should be getting an answer of 3.14 inches squared for area 1. Area 2, you should be getting an answer of 28.3 inches squared. And now check your work to make sure you're absolutely correct here, because remember, a radius of 3 is a diameter of 6. Okay, so we've got at least that portion of the problem correct. So now, what is the pressure in this system when 400 pounds is applied to an area of 3.14 inches squared. Okay, so we've got to use our FPA triangle, and we want to find P, so it's force divided by area. P is equal to force divided by area, which is equal 400 pounds in this example, divided by 3.14 inches squared, which should give you an answer of 127 pounds, 127.4 pounds per square inch. What's the pressure in this chamber? Well, same thing, because according to Pascal's law, pressure in a confined system is transmitted undiminished in all directions. So now that means the pressure of 127 pounds per square inch is acting in every direction on the area of disk 2, which is incredibly large, of 28.3 inches squared. Okay? So what is the force being applied to upwards by the disk of area 2? Well, force, whoops, I've already written it, I don't need to write it twice. Force is equal to pressure times area. We've got our area, we've got our pressure. Our area is 28.3 inches squared times our pressure, 127.4 psi. Going to give us an incredible force of 3,661 pounds. Not too shabby, huh? For only putting 200 pounds in, or excuse me, 400 pounds in, we get 3,661 pounds out. But keep in mind, the travel for our first disc, it only went down an inch. So how much volume of fluid have we displaced in that first cylinder? Well, what was our area? It's 3.14 inches squared. Traveling down 1 inch implies 3.14 inches squared times 1 inch. We've displaced 3.14 cubic inches of space. Now imagine spreading 3.14 cubic inches. I know it traveled an inch for that small area on an area that big, 28.3 inches squared. I mean, just think about this. Take a Coke can and try to fill up another Coke can. Obviously, it's going to fill it. Try to take a Coke can and fill up an empty pool with it. It's certainly not going to reach the top of that pool. That's exactly what's happening here. You're going to get this incredibly thin, i.e. small displacement when that same volume of fluid is spread out over an area of 28.3 inches. Okay, so how do we determine that? Well, 28.3 inches squared divided by, whoops, that's not going to work, 3.14 cubic inches divided by 28.3 inches squared is going to give us 0.111 inches of upward travel. Okay, you get it? Get how I did that? 3.14 inches cubed divided by 28.3 inches squared. The squared, those inches get removed, so you're left with 1 inch. So it's only goes up 0.11 inches. Okay, so let's refer ourselves back to what we originally asked. What is our energy or work accomplished by this system? Well, we did we lifted with a force of 3,661 pounds, a distance of 0.11 inches. What is the work accomplished by the system, 406.2 foot-pounds of work. Which, if you are a very astute person, is a totally wrong answer. So, where's the error here? Notice the unit foot-pounds. Okay? Foot-pounds. What was the vertical displacement of that disk? 0.111 inches. So the reason why I did this way is to illustrate a very, very, very common error with especially the English system here. You know, this displacement of, in our particular case, cubic inches. We could have used gallons. What is the unit of energy in the English system is foot-pounds. It's not inch-pounds. So we got to go ahead and find a means of conversion. Okay? So, and it's real simple. What is 0.111 inches when it's converted to feet? Well, 12 inches per foot. Those inches cancel out because, again, we're multiplying by 1. We're left with feet. So 0.111 divided by 12. 0.00924 feet. So now how many foot-pounds of work have we accomplished? 0.00924 feet times 3,661 pounds. The correct answer, 33.85 foot-pounds. And let's say, what was our power requirement? So we did this in 2 seconds. How powerful is that system? .93, or how fast do we accomplish that work? So in 2 seconds, so we did 16.93 foot-pounds per second. That's our power, okay? Now, does this all make sense to you here? You know, this is a perfectly ideal system. The energy we got out, the work accomplished was 33.85 foot-pounds. Yes, we lifted with a force of 3,661 pounds, but we only lifted an incredibly, incredibly small distance. And how much was the energy that you put in here? You know, 400 pounds for a displacement of 1 inch, which we know is 1/12 of a foot. That's roughly 33.3 foot-pounds of energy. And due to rounding errors, yeah, we got 33.85 foot-pounds out. They should be equal, you know, so energy in, energy out, same thing. So it's pretty neat. This is, again, a totally idealized system with no frictional losses or anything like that. So energy in, energy out. We could go ahead, if we wanted to, convert this into a horsepower. What is the horsepower requirements of such a system? But again, it would be incredibly, incredibly low, because 16.93 foot-pounds per second, and if a horsepower is 550 foot-pounds per second, so it's not even a horsepower, it's 0.03 horsepower. Okay, again, that seems like a super complicated example, but you have all the techniques to do it. All we did was determine area with something a diameter, determine area with something a radius. We determined a volume that was displaced by 1 inch of travel. We just determined the travel based on the volume. And that was all hydraulics math. That was pretty easy stuff. And we threw in a little loop there because we had to convert feet to inches, inches to feet, excuse me. And then we made use of Pascal's Law, which states that pressure inside an enclosed system was transmitted undiminished in all directions to figure out what the force was on the second disk. Okay, again, so this is a force multiplication system and illustrating some of the hydraulic fundamentals and Pascal's Law. We're going to be revisiting this throughout labs and a number of examples and problems throughout the course. So I suggest you guys please become very familiar with this.